Welcome to a structural design video from the Ultralight Airplane Workshop. This video is part of a series of videos that I'm doing to help supplement the design videos I'm doing for the UWS-4 Ultralight airplane. The structural design series is similar to the aerodynamic terminology series I did. So the purpose is to help provide more information so I don't have to keep explaining things over and over in the more detailed and specific design series that I'm doing on the UWS-4. In this particular video, we're going to talk about doing shear and moment analysis on a cantilever wing spar, or at least on the portion of the wing that is cantilever. For example, if you have a strut braced wing, outside of that strut attachment to the wing, that's going to be cantilever. So this video will apply to that portion of a wing. And by the way, in this video, I'm doing a little experiment with different backgrounds for the slides I'm going to be showing. If you hate it, let me know. If you think it's better, let me know. So here's an example of where the spar is placed on the UWS-4. Typically, you're going to be placing this spar at the thickest part of the wing if you're doing a cantilever design wing. If you're doing a strut-braced wing, you might move it a little bit farther forward, particularly if you're doing a rear spar also, and that rear spar is going to be carrying a fair amount of the load. And you also generally want that spar to be somewhat close to the 25% chord of the wing, somewhere between 25-30%, something like that. And that's because the pitching moment of the wing is generally going to be somewhere about that 25% chord. So you don't have to worry about this spar carrying quite as much beam load because it would have to carry part of the torsion load of the wing. But that's not really what this video is about. So we're more concerned about how the span loading of the wing is going to apply the shear and moment forces to the wing. Now, just in case you're not familiar with spars, particularly aluminum structure spars, so I'm going to talk about a few examples of ways that structure might be built and explain some of the terms. Now, these would typically be some possibilities for an aluminum structure, although I did leave out a box structure, which also would be possible. But here would be the length of the spar running this direction. Here would be the height of the spar. And so you might think of leading edge this direction, trailing edge back this way, possibly. It could be the other way around too. So this up here would be a spar cap. This down here would be a spar cap. This vertical in here would be the web. So your spar caps handle the compression and tension forces, and your shear web is going to handle, as the name implies, the shear forces. We'll talk a little bit more about what shear is here in a minute. But here's some possible examples of how to construct a spar. Now, a spar is not going to have the same compression and tension forces out along its span. So you can actually have a beefier spar toward the fuselage and almost a non-existent spar out toward the tip. And so I'm showing here some various ways that you can have a beefier spar at this end. So the end closest to us here would be more like close to the fuselage. Out here would be closer to the tip. So for example, here where we want it beefiest, we've got a couple of angles here. We've got a bar here. And you can see this front angle is only going a little ways out. This bar is going a little bit farther. And then this back angle is going all the way. So we've actually increased the strength of the spar cap in 3 areas, in 3 steps. And then here's another way of doing it. In this case, there's only 2 steps, but you could double up your angles. That's another way of doing it. Although this is a little bit more difficult, generally because the cross-section area of these angles has a rounded corner on the inside corner, which means on this inner angle, you would actually have to remove some of this sharp corner so that it would fit comfortably in there and make good contact with both faces on both of these angles. Now here's another way of doing it that requires more work than over here. So we have 4 steps here, and this front angle has been cut down in 4 different steps. So out here, it's more like the bar here. And another thing, we've got 2 different sized angles here. You can see that this one is thinner than this one is here. So you could have combinations of different sized angles in the front and the back. And in fact, we could have done a cutaway out here to help reduce the cross-sectional area here, and that would have given us 5 steps coming out there. Now over here, this is where we did away with steps and we did a gradual change in the size of this angle. Now, of course, this only has 1 angle in it, so it doesn't have nearly as much cross-sectional area as this one over here. So it'd have to be a lighter bending load on this beam. And I really didn't show any difference in some spar webs, but you can have quite a few different configurations of spar web too. So for a wooden spar, you can actually have some of the generally same ideas. So let's take, for example, this one out here. Now, generally, you won't have an angle in here. You'll have more of either a rectangular or a square block of wood, and you might even have wood on both sides. but doing a step like this would make quite a bit of sense. And in wooden spars, a box spar, which I'm not showing here, also makes a lot of sense. But since this is to help support the UWS4 video series, and we're using aluminum, I'm really concentrating more on that here in these structural design videos. So I want to try to answer the question of why to do these calculations. I'm sure some viewers looking at the UWS4 series are thinking, man, you're doing way more analysis than you need to do. And I suppose you could use trial and error. For example, I could take a wild guess at how the structure of the spar should be, go ahead and create the spar, go out and do a test on it, loading it up to 3.8 Gs with a reasonable distribution, although if you haven't done the calculations, figure out what the span lift distribution is, then you wouldn't know what reasonable is. Let's say for the structure you want to do trial and error. You could go out and do a test. If it fails, then you're going to beef it up some more. If it fails again, you're going to beef it up some more. So you could do that. It'll take quite a bit of time. You may end up wasting a lot of material, but it's possible to do that. But I'd rather not waste a lot of material. I don't have a lot of money to waste on this airplane. I'd like to try to get it right the first time. So we're going to calculate the shear and moment forces on our wing spar. So what is the shear and the moment forces? Let's talk about these shear and moment forces individually. So why do we need the shear? That's going to help us figure out the thickness of our web, and it'll help us figure out for the shape that we choose for our shear web, whether that shape is going to work, whether it's going to fail. For example, in a lot of airplanes, a shear web has large cutouts, circular cutouts in it to help save weight. It's generally solid in toward the fuselage, and it's got cutouts that get bigger and bigger as you go out toward the wingtips. So how big can those cutouts be and still have it handle the shear load? And we'll talk a little bit more about shear load here in a moment. Now, shear is expressed in force per length squared, and that would be, for example, pounds per inch squared. Now, why do we need to know about moment? And I'll explain about moment a little bit more here too. But we need to know what the cross-sectional area is going to be for our spar caps, so we don't overbuild them or we don't underbuild them. And we also need to know the moment in order to pick bolts that are big enough or not too big. Now, what's kind of interesting is this moment is going to be applying a shear force to our attachment bolts that are going through our spar caps. But we need to know how big these bolts are going to be so that they don't shear when we're applying the moment. Now, moment is expressed in force per length. An example of that is pound inches. Now let's talk about shear or shear stress or shear force. The more formal definition is a force that occurs in a plane that is tangent to the tension or compression stresses. Well, that's kind of vague. Now, if you've dealt with these kinds of forces before, it probably makes a little more sense. But if you're new to it, that doesn't draw a very clear mental picture. So I've added another little bullet down here. So what's happening, you've got a force on one side of the plane that I just mentioned up here that's trying to slide in the opposite direction of a force on the other side of the plane, I mean right against the plane. And that creates a shearing action. And you can kind of see that here. Now I drew this to talk a little bit about what happens when you're in a spar cap, the shear that can happen on a bolt there. So let's imagine that this is part of a spar cap, this is another part of a spar cap, and we're trying to connect them together. Now this is not a good design to do that because it's going to try to twist this bolt. This would go this direction, this would go this direction, try to twist the bolt, but ignore that for this explanation. So what's going to happen is, let's say you've got the plane right here where these two spar caps meet. And so you're going to have a force on one side of that plane that the bolt is acting on in the opposite direction. So you've got a force this way, bolt's trying to push this way to counter it, and then you got the opposite on the other side. So you got a plane here, you got opposite forces on each side of that plane. That is your shear stress. And I'm sure you've heard of scissors being called shears, and you also heard of devices for cutting sheet metal being called shears. It's the same idea. Except in this case, let's say this is a blade and this is a blade on the shears, and they're open, so you'd have a gap down here. When they come together, there's going to be that plane right there, and when they start pushing on the material that was in that gap, it's going to put a shearing force on that material and try to cut it. Now we're kind of leading up what's going to happen for shear force in beams, but one little quick aside, torque tube. Torque tubes use a shearing force to transfer force along the tube. Now, if you had any other kind of force in that tube, it would be a tension or compression force, and that would be a parallel to the axis of the tube. So up here we said that the plane would be tangent to your tension and compression. So tangent to the axis would be slicing straight through the tube. So it'd be kind of like the circle here, this dotted circle would be the plane slicing through the tube, and so your shear forces are going to be acting in opposite directions on each side of that plane. So if you're trying to apply a force here, you're trying to hold it on this side, then you're going to have a shearing force like this on one side of the plane, like this on the other side of the plane. So that's going to lead us up to this beam, kind of like the spars in our wings. So let's say we have a fuselage over here that's holding our beam, our spar. We have a load. Now in this case, we're just going to talk about a point load instead of a distributed load. Let's say out here on this end of the beam, we have a load pushing up. So in that case, we're going to have compression here in the top and tension here in the bottom. Our plane is going to be tangent that, our shear stress plane. So that would be this box here would be a plane, and here this dotted line is where that cuts through our spar. Since we have a load here, that load is going to be transferred through this spar over here to where the fuselage is. And that load is transferred using shear. So on this plane, we're going to have shear pushing up on one side, down on the other side. So over here where the fuselage is, it'll be pushing down to counteract this force up here. Shear transfers that force through here. Now since we have a point load here, that shear is going to be the same all the way throughout this spar. Now on a distributed load, where we have, instead of a point load out here, we have a load all along that spar, and we have the fuselage. In that case, the shear will increase. It'll be zero out at one end, where we have zero lift on the wing, and it'll be added together as we add more and more lift force that's distributed along here until we get to the fuselage, which is going to be carrying all that shear load. And the next one I think most people are fairly familiar with, and that would be a bending moment, where you have a force out on a beam. You have it fixed on one end, trying to keep it from moving. That's going to create a moment arm, and then that moment then is the amount of force multiplied by the length of that arm. And a lot of us that have used torque wrenches, we're familiar with that idea. Now there's a whole lot more that could be said about bending moment. For example, things like free diagrams, the sum of the forces in the X direction and the Y direction have to be zero so that things aren't moving, but we're not going to get to that in this video. Before we can start working on these forces on our spar, we need to know what the span-wise load distribution is on our wing. Now I'm not going to talk about how to get that here in this video. If you want an example of two different ways you can do it, the UWS4 Aero Design Series, Part 11A, I did an example of two different ways of coming up with the load distribution on the wing on the UWS4. One was the shrink approximation, and the other one was using a program called OpenVSP. In this video, I'm going to assume that you've come up with a span-wise load distribution for your wing on your own. And here's an example of one where here at this point, we're at our fuselage. Out here is our wingtip. This is feet along the span of our wing. And this is the load distribution in pounds per foot. We're going to use this to calculate our shear and bending moments on the wing spar. I use a spreadsheet to do my calculations, and that's really handy if I want to end up breaking this down into really small portions here along the wing. Now if you're more interested in just doing hand calculations, you can actually do that too, just by using larger sections. In fact, that's really easy to do, like along this section here, or this distribution that I've drawn here is almost flat. You could make pretty much these first four sections just one section. And then down here where this is still fairly flat, it's slanted, but still fairly flat, you could probably combine these three together. But then as you get more and more curvature out here, it's better to break it up just a little bit more. But even let's say you had 6 sections you broke this up into, that'd still be pretty easy to do by hand. Now I like to have just a little bit more resolution. I would at least like to break up my segments where the ribs are going to be. But I did more sections here. Now these sections are somewhat arbitrary. In fact, in this particular drawing, this doesn't actually match what I did in the spreadsheet. I did somewhere upwards of 30 sections along here. Well, that gives me a little bit more ease in moving ribs around a little bit later if I want to. Then it's easier to move the calculations around in the spreadsheet. But essentially what I'm doing is I'm taking a segment that starts at a particular Y1, ends at a Y2. And by the way, in the coordinate system we typically use on airplanes, Y is out along the wings, left and right, out from the aircraft. Z is vertical, and X is front to back on the aircraft. That's why I used Y here. So for each section, I have a Y1 and Y2. Y1 is the inner part of the section, Y2 is the outer part of the section. And then Y2 of one section is the same as Y1 of the next section. Then I average them just simply by taking the half the distance between the two. I calculate how much lift there's going to be in there by taking the span-wise lift right at that average and multiplying it by the length along here. That gives me the lift in this little section. And I assume that lift is going to be right here in the middle. Now when we're calculating the moment, we're going to have a reference point where we multiply the distance of that lift from our reference point. That's going to give us our moment. But we'll talk more about that here in a moment. So here's a spreadsheet that I did in Google Docs using the shrink distribution. I did some calculations to make it a little bit easier for me in the future for other wings. I've actually divided the wing up into 3 sections where I have a root chord, a tip chord, the span of that section, and the number of tessellation or the number of subsections I want in there. And I did that in 3 sections where section 1 is attached to section 2 a little bit more outboard, and section 3 would be out at the wingtip. That's just to help me later if I want to do a tapered wing, I could do that. But you can see here all my chords are 5.18 feet, which is what I happen to have on the UWS-4. And I did some calculations for the area of each section and summed that up to make sure it looks right. So that's 124 square feet, so that's about right for me, double the 62. Looked at the semi-span, that's 12. This is just sanity checking to make sure I didn't screw something up here. And I calculated what the average span loading is, because I've got my weight, my load factor, and what the total load is. So I take that total load, divide by the total area, and that gives us the wing loading. So that's wing loading. And then for the span loading, the average span loading, again, we take total load and we divide it by the span. So that gives us our roughly 82 pounds per foot. Now let's talk about our Y1, Y2, and Y average. I mentioned it in the previous slide, but Y1 and Y2, so you can say I have quite a few sections just here in this first section. So Y1 at 0 is at the fuselage, Y2 at 12, that's out at the wingtip. So you can see I'm going in half-foot steps for each of my subsections, and then Y average is halfway between Y1 and Y2. I also put the chord down in here at each one of these sections. Now we got a rectangular wing, so it's going to be the same for all of our subsections. I'm also calculating the planform span distribution at each of these subsections. Now we got a rectangular wing, so for the shrink span distribution, it's going to be the same all along here, since it's a rectangular wing. I'm not going to get into how the shrink span distribution works. We talked about that in part 11A of the UWS-4 design series. But the result over here is our span distribution at each of these subsections. So I'm going to assume that you somehow come up with a span distribution for your wing. So let's start talking about how to calculate our shear, particularly shear in our spreadsheet. So we got some place along our wing where it's being held. Now in our case, it's being held here at the fuselage. If you had a strut-braced wing, it'd be wherever that strut attached to the spar. So how do we figure out that shear stress along the spar? It's actually pretty easy. We go out to the furthest extent on our spar. We calculate how much lift there is here in this section. And we're going to say, okay, that shear is going to be here at the Y1 of that section. The lift and the shear are going to be the same right here for this very first section. Now for the next section inboard, we want to know what the shear is here at this next Y1. Well, it's going to be the weight of the outer sections from that spot. So it's going to be this section and this section. You add those lift together, and that's going to be the shear here at this spot. And just keep doing the same thing. Shear at this spot is going to be lift from all these sections out here. So you can see that the shear builds as you go inboard to wherever your attachment point is. So for example, the shear here at the fuselage is all the lifts out here added together. That's pretty easy to do in a spreadsheet. So here I did a diagram of what the result of our spreadsheet calculation is. And you can see it's almost a straight line. It does have a little bit of curvature to it. So if our load along the wing was uniform, this would be a straight line. But since, if you remember, let's go back and look at it, our distribution tapers off down here. So it starts with small numbers and then it gets bigger numbers as you come inboard. And that's going to actually cause it to start out small and then build more and more. It's still pretty close to a straight line though. But let's talk a little bit more about how I do it in the spreadsheet real quick. So I've got this capital Q, which stands for total shear stress at some particular location along the span. That's what this I is, at some location along the span. A lower Q is local shear stress, or probably more appropriately is load. So shear and the load are closely related. So out here at position 12, your local shear and your total shear are going to be the same. You've only done one section. Let's say you move in one section to position 11, so you're going to have the local shear at position 11 added to the total shear that's outward of that location. So you just keep doing that as you go farther and farther inward. For example, the total shear here at the fuselage is going to be the local shear at, this should be a 0, plus all the shear that's outboard of that. So back to our spreadsheet here. I've got a column here where I calculated the local lift at each section on the wing. So that's going to be each of these sections here, what the lift is in each one of these sections. So you can see it's fairly flat, 46.5 here near the fuselage, fairly flat, and then starts dropping down and gets down to 12, close to 0 here out the wingtip. Now to do a quick sanity check, I want to see if I add all these up, it should match the lift I've calculated for the wing. So 982 pounds would be the semi-wing. You have to multiply those two together, we get 1965. Let's go up to our calculation where I calculated what that total lift is, which is the weight of our airplane multiplied by our load factor. So we're off by about half a pound. So that worked out pretty good. So that was just a sanity check to make sure I hadn't made a mistake in my spreadsheet. So the next thing is a shear column. And let's just start working from the bottom. So this would be our Q12 we just talked about. So they match. Next one in, this would be Q11. So that's going to be the sum of these two together, 25. So 13 and 12, 25. And we just keep doing that. So at the next section up, it's going to be the sum of all three of these. Now I cheated a little bit. What I did in my calculation here, just because it's easier, for example, this one here, I took this plus this. So you just take the previous one, the big Q, add in your local Q, and that gives you what your total Q, your big Q is here. So that makes it much easier to do in a spreadsheet. And why don't I just show it to you here? I just double clicked it to bring this up. So J50, column J, line 50, that's the local one, plus K51, which is this one down here. So I took big Q outboard, added it to local small Q, and that gives us our big Q at our local spot. Pretty easy. Well, now we come to the moment one. Now, moment is a little bit harder to do. Not a whole lot, but a little bit. At least conceptually, it's a little bit harder. Let's talk about moment at one location. Let's pick this location right here. So this is some Y out along the wing, and we're going to have moment, and we're going to call it moment at Y position I plus 1. And that's just a nomenclature to help us a little bit. Next one would have been I. Next one is I minus 1, and so on. So that moment is going to be referenced right here at this line, and it's going to be the load at some location out here on the wing multiplied by the distance of that load from our reference. So that's a moment. So at some point in our spreadsheet, we've calculated this moment at this location. What we want to do next is calculate the moment at the next Y location inboard. So we still have our segments similar to what we did for the shear calculations. In fact, I'm using the same exact division of the spar. So the next reference is here at this line. Now we're going to try to take advantage of something that you can do with moments. You can add moments together as long as they have the same reference location. So we got two moments here. We have a moment for this little section here, so local moment. So that's going to be the lift at that local section at that Y average multiplied by the distance from our reference to that Y average. So that's going to be a little local moment. What we would like to do is take this moment that we calculated out here at this reference and change its reference to this same location. We can then take that moment, our local moment, add it together, and that will give our total moment at that location. Now for calculating our local moment, we already have all that information when we did the shear. We know the distance from Y1 to Y average, and we know the local lift. That one's easy. The harder part is doing that reference change for what we've already calculated out here. Let's talk about how to move that reference from this location to this location. So let's start with our I plus 1 moment from this reference here. Now we already talked about this Q getting the local lift right here. By the way, our local lift and our Q's, the way we segmented this up is the same. That's what I'm trying to say up here. N and Q are the same. Our big N and big Q. We have a big N and big Q. So our N out here, our lift, is the same as our Q right here. Lift at position I plus 1 is the same as the shear at I plus 1. And same thing for our local ones, our lowercase n and q. The lift here in this section is the same as the shear referenced here. That's what these two calculations are on here. Getting the local lift right here at I and the local moment at I. We talked about that. That's pretty easy to do. Well, now we need to actually figure out what this distance here should be. We don't have this calculated right now. All we know is what that moment is and what the shear is. Well, since we have the moment and the shear or lift, we can calculate that distance. Remember, the moment is our lift or shear times length. Let's just rearrange this equation. Take our moment divided by our shear. That gives us our length. So now we've calculated how far out that lift is. That's its L at I plus 1. In this case, L is not lift, it's length. Now it's quite easy to change that moment from here to here. We just add in our y2 minus y1 at this section, add that to our L, and that gives us our total length from this reference now. This plus this will give us our total length. Now, in order to get the moment now from that spot, we multiply our length times that lift. That now gives us our moment changed to this reference point. So that's what I'm talking about here. Add the L to y2 minus y1, that distance here, multiplied by the lift or the shear at I plus 1. Now we have our moment with the reference moved. Well, now that we have that reference moved, we can add our local moment to the moment that we just moved down here. That'll give us our total moment at this spot. And that's what we're talking about here. So the local moment plus the moment where we've moved it equals our total moment. So that's what I did in the spreadsheet. I know this is a little bit difficult to grasp. Maybe it'll help a little bit looking at the spreadsheet. So I have a moment calculation here, and this is going to be total moment at each of our Y locations. Then I got another column here that helps me calculate the next Y location inboard. So let's go out here and start at the tip. So out here at the tip, what's that moment going to be? So out here at the tip, the local moment and the total moment out here at this spot here is the same. So whatever that distance from Y1 to the average is, multiplied by the lift on that segment. That's all it is for the moment. So that is this 1.5 foot-pounds. Now this is that length arm. We just calculated that big L. So that length arm is this value right here, this L. Now it just so happens that for this outer section, that length arm is going to be the exact same thing as the difference between our Y1 and our Y average. So basically 1.5 inches. Now let's go to the next section in. On this equation here, to calculate that total moment, I've added all that stuff we just talked about all into one equation. So I'm basically doing all of this down here in one equation. So we take that L we just calculated on the previous line, we add to that this distance here. So this distance here for our current section, Y2 minus Y1, then that total length there is multiplied by our total shear at this reference line, and then we add our local moment. Now these are actually color coded, so it might help looking at this just a little bit. So the C52 and B52, that's our local Y1 and Y2. That's this one. So here's Y2, here's Y1. We add in our L from the next line down, M53. That's this one down here. We multiply that by our total lift out there, the Q at I plus 1. So that's K53. So that's down here. That's this one here. So that is our Q. So this is the moment moved from its previous reference to our current reference. And now we want our local moment. So that's going to be our Y average minus Y1 multiplied by our local Q. So Y average minus Y1, so that'd be this distance here. Then multiplied by our local force, local lift, our local Q, or shear. Add them together, and that's now 6.22. And just keep doing that on up above. So next section in, this would be the L, the difference on the outer one for this guy. So we're trying to move his moment into where his reference is. Then we move his moment, that length, to here and add them in. And we just keep proceeding upward until we get here to the fuselage where our moment is 5,452 pounds-feet. So conceptually, it's fairly easy. Once you get it into the spreadsheet, it's fairly easy too. Now, it's easy to make some accidental mistakes when you're setting up those equations, but once you get it set up, it's not bad at all. Well, once you get all that done, you can make a chart out of it. And for this little example we're doing, it looks a lot like this. And this is actually fairly close to a typical moment graph for a wing spar. Not bad at all. So you can see we come up close to that 5,500 here at the fuselage, and we go out to 0 out at the wingtip. Now, as I mentioned before, things are a little bit different if you have a wing strut. Now, outboard of this wing strut, it's the same as just talked about, but between the fuselage and the wing strut, it's a little bit different. So that's going to change your shear and moments quite a bit. Things can also change if you're going to have a rear spar that's going to carry some of the load. That's beyond the scope of this particular video. And another thing to consider is that ribs tend to concentrate that lift force where they attach to your spar. So it's not going to be this nice smooth line. It's actually going to be fairly flat in between those ribs, and it's going to jump where a rib is, then come up, jump where a rib is, then be fairly flat all along here. Now, it's not strictly true. There will be some slope in between, but it's a fairly good approximation. And of course, that's assuming you have spar and rib construction. Now, if you have something more like moldless construction, like on the Very Easy, then in that case, you do have a pretty smooth distribution here, except our next point here, where ailerons and flaps will add some point loads to your wing, which is going to change it just a little bit. In that case, wherever your ailerons and flaps attach, if you have small hinges, that'll make jumps here also. Now, if you have hinges that are full span, in other words, a hinge starts at one end of your aileron or flap and goes continuously across, like with a piano hinge, then the load will be distributed okay. But if you have a hinge at one side of your aileron, another hinge at the other side, that's going to add point loads, which will make little jumps here in this distribution. And as I said here, that's assuming we have discrete hinges instead of continuous hinges. So the next thing you would do in your design, now that you've got your moments and your shears, you can start calculating how much cross-section area you need in your spar caps and cross-section area in your shear web. Well guys, that's it for this video. I hope you found it helpful. Until next time.